What you need to know about solid electrolytic capacitors. You don't know. Solid electrolytic capacitors are a type of electrolytic capacitor that utilize a solid electrolyte instead of a liquid or gel electrolyte. This solid electrolyte typically consists of a conductive polymer or a conductive oxide, which serves as the dielectric material between the electrodes. Here's a more detailed breakdown of solid electrolytic capacitors. Construction. Solid electrolytic capacitors are constructed similarly to traditional electrolytic capacitors, with two conductive plates, electrodes, separated by a dielectric material. However, in solid electrolytic capacitors, the dielectric material is a solid instead of a liquid or gel. Electrodes. The electrodes of solid electrolytic capacitors are typically made of a highly conductive material, such as aluminum or tantalum. These electrodes are usually formed as thin films on a substrate to maximize surface area and therefore increase capacitance. Dielectric material. The dielectric material in solid electrolytic capacitors is a solid electrolyte. This solid electrolyte can be made of various materials, including conductive polymers like polypyrrole or polythiophene, or conductive oxides like manganese dioxide. Manufacturing process. Solid electrolytic capacitors are manufactured using a process called electrochemical deposition. This process involves depositing the solid electrolyte material onto the surface of the electrode through chemical reactions. The thickness of the deposited electrolyte layer determines the capacitance of the capacitor. Advantages. Stability. Solid electrolytic capacitors are generally more stable and reliable compared to traditional electrolytic capacitors because they do not rely on a liquid or gel electrolyte, which can dry out or leak over time. High capacitance. Solid electrolytic capacitors can achieve higher capacitance values compared to other types of capacitors of similar size due to their compact design and the use of high surface area electrodes. Low ESR. Solid electrolytic capacitors typically have lower equivalent series resistance, ESR, compared to traditional electrolytic capacitors, making them suitable for applications requiring low ESR values. Applications. Solid electrolytic capacitors are commonly used in various electronic devices and applications where reliability, stability, and high capacitance are important factors. They are often found in power supplies, audio equipment, telecommunications devices, and automotive electronics. Disadvantages. Cost. Solid electrolytic capacitors can be more expensive to manufacture compared to traditional electrolytic capacitors due to the specialized materials and manufacturing processes involved. Voltage limitation. Solid electrolytic capacitors may have lower voltage ratings compared to other types of capacitors, limiting their use in high-voltage applications. Temperature sensitivity. Some types of solid electrolytic capacitors may exhibit temperature sensitivity, affecting their performance at extreme temperatures. Overall, solid electrolytic capacitors offer several advantages in terms of stability, reliability, and high capacitance, making them suitable for a wide range of electronic applications despite some limitations. The construction of solid electrolytic capacitors involves several key components and steps. Electrodes. Solid electrolytic capacitors typically have two electrodes, one anode and one cathode. These electrodes are usually made of highly conductive materials like aluminum or tantalum. The choice of electrode material depends on factors such as desired capacitance, voltage rating, and application requirements. Dielectric material. The dielectric material in solid electrolytic capacitors is a solid electrolyte. This solid electrolyte can be made of various materials, including conductive polymers like polypyrrole or polythiophene, or conductive oxides like manganese dioxide. The dielectric material is deposited onto the surface of the electrode through a process called electrochemical deposition. Substrate. The electrodes and dielectric material are typically deposited onto a substrate, which serves as the physical support for the capacitor structure. The substrate is often made of materials like ceramic or glass, providing mechanical stability to the capacitor. Electrochemical deposition. The process of depositing the solid electrolyte onto the electrode surface is crucial in the construction of solid electrolytic capacitors. This process involves immersing the substrate with the electrode into a solution containing precursor materials for the solid electrolyte. An electric current is then passed through the solution, causing a chemical reaction that deposits the solid electrolyte material onto the electrode surface. The thickness of the deposited electrolyte layer determines the capacitance of the capacitor. Encapsulation. Once the solid electrolyte material is deposited onto the electrodes, the capacitor is usually encapsulated to protect it from environmental factors such as moisture, dust, and mechanical stress. The encapsulation material is typically a non-conductive resin or polymer that provides insulation and physical protection to the capacitor. Termination. Finally, the capacitor is terminated with external connections, usually in the form of metal leads or terminals. These terminations allow the capacitor to be soldered onto a circuit board or connected to other electronic components. Overall, the construction of solid electrolytic capacitors involves precise deposition of the solid electrolyte material onto the electrodes, encapsulation for protection, and termination for external connections, resulting in a compact and reliable capacitor structure suitable for various electronic applications. The electrodes in solid electrolytic capacitors play a crucial role in their operation. These electrodes are conductive materials that serve as the positive, anode, and negative, cathode, terminals of the capacitor. Here's a closer look at the electrodes in solid electrolytic capacitors. Anode and cathode. Solid electrolytic capacitors have two electrodes, the anode and the cathode. The anode is typically made of a valve metal such as aluminum or tantalum. Valve metals are metals that form a stable oxide layer on their surface when exposed to oxygen. This oxide layer acts as the dielectric material in the capacitor. The cathode is usually made of a conductive material, such as a conductive polymer or a conductive oxide. High surface area. The electrodes in solid electrolytic capacitors are designed to have a high surface area. This is achieved through various manufacturing techniques, such as etching, sintering, or using porous structures. High surface area electrodes increase the capacitance of the capacitor by providing more surface area for the formation of the dielectric layer. Formation process. Before the solid electrolyte material is deposited onto the electrodes, the anode undergoes a formation process. This process involves applying a voltage to the anode in an electrolytic solution, which forms a thin, uniform oxide layer on its surface. This oxide layer serves as the dielectric material in the capacitor. The cathode may also undergo a similar formation process depending on the specific type of solid electrolytic capacitor. Substrate. The electrodes are typically deposited onto a substrate, which serves as the physical support for the capacitor structure. The substrate is often made of materials like ceramic or glass, providing mechanical stability to the capacitor. Interconnects. The electrodes are connected to the external circuitry through interconnects, which are usually metal leads or terminals. These interconnects allow the capacitor to be soldered onto a circuit board or connected to other electronic components. Overall, the electrodes in solid electrolytic capacitors are designed to have a high surface area, undergo a formation process to create a stable oxide layer, and are connected to the external circuitry through interconnects. These electrodes play a critical role in the performance and reliability of solid electrolytic capacitors in various electronic applications. The dielectric material in solid electrolytic capacitors serves as the insulating layer between the electrodes, allowing the storage of electrical energy. Unlike traditional electrolytic capacitors which use liquid or gel electrolytes, solid electrolytic capacitors employ a solid dielectric material. This dielectric material is typically a conductive polymer or a conductive oxide. Conductive polymers, such as polypyrrole or polythiophene, are commonly used as dielectric materials in solid electrolytic capacitors. These polymers are organic materials that exhibit both electrical conductivity and flexibility. Conductive polymers offer advantages such as high conductivity, low equivalent series resistance, ESR, and good thermal stability. They can be deposited onto the electrode surface using techniques like electrochemical polymerization or vapor deposition. Conductive oxides. Another type of dielectric material used in solid electrolytic capacitors is conductive oxides, with manganese dioxide being the most common choice. Conductive oxides are inorganic materials that exhibit high electrical conductivity. Manganese dioxide is particularly favored due to its stability and compatibility with electrode materials like tantalum. The deposition of manganese dioxide onto the electrode surface can be achieved through processes like chemical vapor deposition or electrodeposition. Formation process. The dielectric material undergoes a formation process during capacitor manufacturing. This process involves depositing the solid electrolyte material onto the electrode surface through chemical reactions. For example, in the case of conductive polymer-based capacitors, electrochemical polymerization is used to form a thin layer of polymer on the electrode surface. Similarly, in capacitors using conductive oxides, the oxide material is deposited onto the electrode through processes like electrode deposition. Properties. The dielectric material in solid electrolytic capacitors is characterized by properties such as high electrical conductivity, stability over a wide temperature range, low ESR, and compatibility with electrode materials. These properties contribute to the performance and reliability of solid electrolytic capacitors in various electronic applications. Advantages. Solid electrolytic capacitors offer several advantages over traditional electrolytic capacitors, including higher capacitance values, lower ESR, and improved reliability due to the use of solid dielectric materials. Solid electrolytic capacitors are often preferred in applications where space, weight, and reliability are critical factors. In summary, the dielectric material in solid electrolytic capacitors plays a crucial role in enabling the storage of electrical energy while offering properties such as high conductivity, stability, and compatibility with electrode materials. Conductive polymers and conductive oxides are the two main types of dielectric materials used in solid electrolytic capacitors, each offering unique advantages and characteristics.